This is a report on MATLAB exercise number 1, modeling in frequency domain using symbolic math. So 4 exercises were given. First is about the inverse Laplace transform. Second is about the Laplace transform. Third is about the transfer function. And finally, Cramer's rule. Now for the Cramer's rule, there is a problem for the initial solution. So in my initial solution, I directly substituted R1, R2, L, and C with 1. So this is the resulting matrix, as well as B2. However, the problem with this is by running this whole command, it gives the incorrect answer for the transfer function. So to fix this in another code, what I did was retain everything from the very first series of commands. But I added a new line after the sims command, which states that all R1, R2, L, and C will be set to 1. So as a result, by running this command, it chose the right answer. So in conclusion, symbolic math made it easier to solve inverse Laplace transforms and Laplace transforms. For example, a very tedious part is solving, for example, this s all over s squared minus 2s plus 10. This results in the following. While a typical student would take on average 3 minutes or say 2 minutes to solve a question such as this, because of the partial fraction part, the computer does it in record setting time, as expected of a computer. Uh, One notable thing to be discussed is how they frame large parentheses such as this one, which is at first glance it is an eyesore. And moreover, these multipliers, which are all in the end, can throw off anybody who uses the commands because traditionally it is written in the very first part. So it's not e raised to negative 2t times the function times 3. It's supposed to be 3 times e raised to negative 2t times the whole function. Although it's the same answer for both, one is surprisingly more convenient to be expressed than the other. This is the same as in the Laplace transform. Next, when it comes to the transfer functions, I find that every Laplace transform is already or almost uh, expressed in terms of the transfer function itself. The difference being that if there was a simplifiable in the denominator, especially, and also in the numerator, this can be expressed easily as poles and zeros. There is a additional functionality in the very end where you can actually show the poles and zeros of the specified answer. Finally, applying Cramer's rule requires an additional analysis. You simply do not have the circuit itself, and from there, the MATLAB will solve it for you. You have to express each as a series of equations by hand and then express them in terms of a matrix. So, although it does make it easier to solve for the transfer function, wrong analysis of the circuit part, or in that case, any other dynamic systems, will result still in a wrong answer, which does not put the whole job on the computer itself, but still requires an intelligence from the user or the calculating person. And this concludes my report.